Hey guys, welcome to part 2 of the Magnetism series. In this video, we're going to focus specifically on the Lorentz force. Now, many actually refer to the Lorentz force nowadays as just the magnetic force, but it is a phenomenon that is named for Dutch physicist Hendrik Lorentz. His findings are what have created the two equations that we will cover in this video today. Now, the image that you see on the screen right now is a snapshot from an interactive tutorial from the nationalmaglab.org. It's from their Lorentz force interactive page. Now, in this image, you see a circuit. The circuit has a battery, a knife switch, a permanent magnet, and a contraption that is near the permanent magnet that is basically a wire pendulum. You can think of this little piece here as almost like a trapeze swing. It swings in and out between the poles of that horseshoe magnet that's laying on its side. Currently, the switch is open, so there's no current running through the wires. Now, it's important to note that the wire pendulum is hanging naturally as if the magnet weren't even there. Now, when the knife switch is closed, a current is running through the wires, and thus the wire pendulum. Here's a picture of what happens when the switch is closed. You can hopefully see that the wire pendulum has swung towards the curve of the horseshoe magnet. When the switch is opened again, the wire pendulum falls back to its natural space. Next, let's change the polarity of the battery and close the switch again. What we see now is that the wire pendulum has swung outwards away from the curvature of the horseshoe magnet. At this point, I recommend that you pause the video, list out some observations, and then try to come up with some reasons as to what is happening here as this wire pendulum swings when there is a current running through it. When you're done, come back to the video and we'll take a look at what's actually happening here. Let's go back to the first situation where the switch was open and the wire pendulum was hanging at rest. Right now, if we were to draw a force diagram for this, we would say that there's really only a gravitational force pulling down on the orange bar, and there is some tension on each green wire that's pulling up, keeping the bar at rest. Now, when the switch is first closed, the wire pendulum swings towards the curvature of the horseshoe magnet. This implies that there's a force acting now that was not acting before. So let's determine where that force is coming from. Now, if the horseshoe magnet was not there and we connected or closed the switch, we would have current running through the wires like we've studied before in electricity and circuits, but there really wouldn't be any other sort of outward observation that you could make that there was current running through the wires. Now, in the presence of the magnet, however, there is some sort of interaction between the wire pendulum and the bar magnet itself. This implies that there is a magnetic force that's interacting with this charge. We could go even further to say that the magnetic force only interacts with the charges when they are moving. If the charges are stationary, as when the switch is open, there is no magnetic force interaction between the wire pendulum and the magnet. We can go even one step further and say that we know the fact that the charge is moving interacts with the magnet to produce a magnetic force, because when the battery polarity is flipped, the wire pendulum pushes in the other direction. This implies even further that the moving charge's velocity, which includes their direction and speed, are important to this interaction. Now let's start to develop an equation that can describe this interaction. Let's go ahead and simplify the current down just to a single moving charge moving through the wire pendulum bar. We know that when there's velocity of that moving charge, which we're extrapolating here from the current, we will experience a magnetic force. Now, we didn't look at it in this simulation, but I can vouch for it and say that when the current is higher, the pendulum wire swings further, which implies that the current is somehow directly proportional to the magnetic force, and therefore the individual charge's velocity is directly proportional to the magnetic force. Another interesting point is that if we leave the battery polarity the same, but we flip the bar magnet, we will see that the wire pendulum swings in the opposite direction than before. So it becomes very apparent that the direction of the velocity and the direction of the magnetic field with respect to one another actually influences this magnetic force. We'll get into that in a little bit more detail later in this video. Now, before we move on to that idea, let's focus on this factor of the velocity as related to the current. Now, we know current is defined as the amount of charge passing a point in a wire in a given amount of time. So the velocity of the charges is not enough to represent the current. We'd also actually have to have the magnitude of that individual charge. So putting all of these proportions together, we see that the magnetic force is dependent upon the product of the charge times its velocity times the strength of the magnetic field. We can describe the current in the wire as relating to the magnetic force by saying that the magnetic force is equal to the product of the current times the length of the bar times the magnetic field. Try to see if you can figure out the relationship between both of these equations and how you would derive the one from the other. For sake of time, I will not cover that in this video. At this point, it's very important for us to consider the directions of the magnetic field, the velocity of the charged particle, and the resultant force. If I were to set up this apparatus again, however, if I was to make the wire pendulum parallel to the horseshoe magnet, I would not see any effect on the wire. In other words, I would not see the wire pendulum swing. So let's draw in the directions of the current, or the individual directions of the velocity of the moving charges, as well as the direction of the magnetic field, and take a look at how they're oriented towards one another. Finally, we can draw in the direction of the magnetic force based on the direction that the pendulum wire swings. So in this original orientation, we see that the magnetic field lines between the ends of the horseshoe magnet point from north towards south, so straight up in the vicinity of the wire pendulum. The current, or the velocity of the individual moving charges, will point perpendicular to that magnetic field. When the switch is closed, we can see that the wire pendulum is forced or accelerates in the direction towards the curvature of the horseshoe magnet. That implies that the magnetic force is pointing towards the curvature of the horseshoe magnet, once again perpendicular to both the direction of the magnetic field and the direction of the velocity of the charged particles. It's at this point that we introduce what is known as the right-hand rule. The right-hand rule is a way to figure out the direction of the magnetic field relative to the velocity relative to the magnetic force. Now keep in mind, they're all at right angles to one another. If the fingers represent the magnetic field and the index finger represents the direction of the velocity, then I can rotate my whole hand, and my thumb, which is perpendicular to both my three fingers and my index finger, will point in the direction of the magnetic force. Because we're working in 3 dimensions now, we're going to add some extra notation to help us be able to represent 3 dimensions on a 2-dimensional page. We often use x's as a vector or an arrow pointing into the plane of the page. We use dots to represent the vector coming out of the plane of the page. We might traditionally call this the positive and negative z-axis. We therefore will represent the y and the x-axis the same as we always do, and have this extra x and dot notation to show into and out of the page. Let's take a look at an example. Here I show a magnetic field that is uniform and is pointing into the plane of the page. I know this because I have a series of x's that are labeled b. I then show a velocity vector of a positive moving charge moving from right to left, or in other words, pointing to the left-hand side of the screen. So if I orient my right hand with the 3 fingers pointing into the plane, with my index finger pointing to the left, my thumb is left pointing straight down towards my body. That implies that the magnetic force would be down on this charged object. Here's an additional example for you to pause the video and try to figure out on your own. Here we can see that the magnetic field points out of the page, so I'll orient my 3 fingers pointing up towards the ceiling. I will then place my index finger pointing in the direction of the velocity of the charged particle, which is up, away from my body, leaving my thumb pointing to the right. So the magnetic force that would be acting on a charged particle that's moving in this direction relative to the magnetic field would feel a force pulling it to the right. We'll get into that in a lot more detail in the next video. We end this video by taking a look at the mathematical ramifications of the direction. If the velocity and the magnetic field are parallel to one another, we see that there is no magnetic force. This implies that when the velocity and the magnetic field are perpendicular to one another, we have the greatest magnetic force possible. If we go back to the equation that we structured before, force is equal to Q times V times B, something should hopefully ring a bell. This is actually a cross product between V and B. In other words, I only multiply the perpendicular component of V with B. This means that I would actually have to add sine of theta, or sine of the angle between B and V, into my equation. For shorthand, and to demonstrate the direction of the magnetic field, I would just use the cross product. The cross product comes into play when I don't have a 90-degree angle between the velocity and the magnetic field. In other words, let's say I have a situation that looks like this. Here we can see that the velocity is not perfectly perpendicular to the magnetic field. Now, we don't have to bend our fingers in this right-hand rule. In fact, we never will. We will always keep our fingers at a right angle to our index finger, at a right angle to our thumb. We will just state that only the component of the velocity or the component of the magnetic field that is perpendicular to the other actually affects the magnetic force. It's very similar to torque. In torque, we described that only the perpendicular component of a force and a position vector would cause a torque. It's the same idea here. Mastering the right-hand rule just takes some practice. It's not really that difficult, but it is a little bit mind-warping when you first start to think in 3 dimensions using your hand. The last thing I'll note is that if you're dealing with a negative charge, we would use the left hand instead of the right hand. The reason for this will become apparent in a subsequent video. However, if you have an electron entering a magnetic field, we would use the left hand, and therefore the only difference would be that the force points in the opposite direction than it would if we used the right hand. We'll stop there for this video, and in the next video, we'll take a deeper look at what the ramifications are of a force that is perpendicular to the velocity vector of a moving charge. We'll also compare and contrast what we know so far about the magnetic and the electric fields.